Sorry. So we'll start the session now. Hello everyone. So today we are going to discuss about the weekday lectures that I hope you guys have gone through. So today we'll be discussing about the routing methods and what is routing and so on. Okay, so just to start with, hello everyone. Today we are going to discuss about the week 10 lectures of the course, that is Watershed Hydrology, given by Professor Rajendra Singh from IIT Kharagpur. I am Balram Shah. I am the PMRF TA for this course. I am doing my PhD at Interdisciplinary Center for Water Research at Indian Institute of Science, Bangalore. So with that, let's start with the question ones. Okay, before moving on to the questions, we'll just see what all contents we have seen, and in between we'll do the question answers. Okay, I'll share it from here once. Give me a minute. And just for the recording, I'll switch off the video so that bandwidth does not be the problem. Sure. Yeah, I hope you guys can see the screen. Right. So before moving on to the questions, let's just see what all we have learned. Starting with, so what we have learned in this course, starting with the word routing. Anyone, what do you mean by routing? You see, in this, the term only, it is made of root plus ing, right? So it's like some we are moving through a route and we'll be doing something on the route of the streams, right? So in this we have mostly study about flow routing. What is flow routing? Flow routing is a procedure to determine the time and magnitude of flow. Flow as in the flow hydrograph at a point on a water course. From known or assumed hydrographs at one or more points upstream. So I wrote the whole definition so just because you guys can understand it better. So here what we are seeing is flow routing. Flow routing as in, so let's say if you know about some information, here we are as in the information we are talking about the hydrographs that we have studied. So if you know the hydrographs at one or let's say more than one points in the upstream side, so let's say you know the hydrograph here, you know the hydrograph here, and you know the hydrograph here, let's say. So all these hydrographs are known, right? And you want to, let's say, do something here at this point, at this location where I have pointed out with the black marker, right? So here, for doing anything here, so let's say if you want to make a reservoir or something important you want to do on the river streams, right? So in that case you don't have the data or hydrograph directly at that point. So what you can do, you can use these information as in where you have the hydrographs to construct or to create a new or to develop a new hydrograph at the location or at the downstream section, right? So this process of determining the time and magnitude of the flood or the flow at a point. So time and magnitude as in the flow hydrograph, basically we are talking about at a point on the water course from known or assumed hydrographs at one or more points upstream. We call that as flow routing, right? And now most in the lecture you might have heard about, you have started about flood hydrograph or flood routing. Right. So flood routing is when, so let's say if the flow is a flood, because not always we have a flood, right? So if the flow is a flood, then the routing procedure is called, the procedure is specifically known as flood routing. Okay. So let's say if in a broad sense, if you see, in a broad sense, flow routing may be considered as an analysis to trace the flow through a hydrological system. So what we are doing, we are tracing the flow through a hydrological system. So here the system is what? Here the system is a catchment. And what we are doing, we are tracing the hydrographs at some of the location that we need. And hence what we are saying that flow routing is an analysis to trace the flow through hydrological system where the inputs are given. Inputs as in the hydrographs where the known hydrographs, let's say. Okay. So so with this we'll start the flood routing system. Okay. So let's say the hydrographs, the known hydrographs are like, let's say you have the hydrograph for one location, you have the hydrograph for the second location, and one hydrograph for the third location, something like this. And here, with those information, you will get a new hydrograph. Okay, so flood routing generally, what we do, we study how the flood waters propagate through a river system. So it will help the like hydrologist and all to understand how the water movement is varying, like what are the impacts of these water movement or the flow to the infrastructure, or how effectively we can manage and mitigate the flood risk when we talk about flood routing. Right? So it involves the computation of movement of flood wave along the channel with time and space. Now, this flood routing can be classified into two groups. First is the reservoir routing, and the second one is the channel routing. Okay, so both these routing methods are different approaches which we use in the flood routing to understand the movement of the water through river system during any flood events, because we are talking about the flood routing. In the reservoir routing, what we study the flood waters how it propagates through a reservoir or let's say any structure such as dams, other than reservoir if you talk about. Right. So mostly this reservoir routing we talk when we have a large water body, maybe dam or reservoir, anything. Okay. So this reservoir routing is very important when we need to decide the location, like where we want to create one dam or something like that. Right. Then we need to understand what will be the capacity for designing the reservoir and all. What is the capacity of reservoir, such as what is the shape, size, and all of the reservoir to meet the specific requirement. So, what are the key components which is needed for reservoir routing? Firstly, we have to do the inflow outflow analysis, right? So in inflow outflow analysis, what we do, the reservoir routing involves the analysis of flows into reservoir, including direct precipitation, runoff, then other contribution from upstream tributaries. And the outflow from the reservoir is controlled by operation of gates, spillways, or other hydraulic structures. Okay, so this is one of the key component is inflow and outflow analysis. Second is the storage discharge relationship. Okay, so we might have seen in the lectures that this reservoir routing it establishes the relation between the storage volume of the reservoir and the corresponding outflow. This relationship, that the storage and discharge relationship, we have studied before also in the lectures, that for any reservoir that we have, right, for those we will have one storage discharge relationship, so that it will help us to understand how the storage volume of the reservoir is there for some value of outflow, right. So this relationship is very important to predict how this storage change due to the inflow and outflow influence the discharge in the downstream section, so that we can take any decisions based on that. Okay. Okay. Now coming to the effect of reservoir on a flood hydrograph. So effect of reservoir on a flood hydrograph. This is a very important concept. Just we'll see that. So let's say, as I said, the inflow outflow is no. Okay, so this is the hydrograph. Let's say discharge. Q. This is 10 T, let's say. Okay, so let's say this is the inflow hydrograph, something like this. Okay, and this is the outflow hydrograph, let's say. Okay, now you see what all differentiation you can see between this inflow hydrograph and outflow hydrograph. I'll write okay, I'll write this. This is inflow hydrograph and this is outflow hydrograph. Yeah, so can you tell me what all difference or what all different things you can see in the inflow hydrograph? How different is the outflow hydrograph from the inflow hydrograph? Firstly, in the time you can see. You see the peak happened in the inflow here, whereas the peak in the outflow happened here, right? So you can see there is a time lag between these two peaks. So we call that as lag, right? So first difference is in the time domain. That is how the peak in the outflow we can see later than that of the inflow hydrograph, right? Other than that, can you see anything? If you see in the discharge domain also, you see the peak happened at a very higher discharge, whereas in the outflow peak is at lower value. So this you can see there is a attenuation. Attenuation as in there is a decrease in the peak. Okay, so we have one attenuation. So we have lag of peak, or I'm like peak occurrence, let's see, right? And then attenuation of the peak. Anything else you can see? So there is third difference is the lengthening of time base. You remember what is time base? The total time that is required from the starting of the hydrograph to the end of the hydrograph, that we called as time base. Remember? So the length of the time base will also vary in the outflow and inflow hydrograph. Okay. So let's say, okay, we'll come to that later maybe. Okay. So this was the effect of reservoir on a flood hydrograph. Okay. Next, what was there? We had channel routing, right? So we'll talk a little about channel routing and then we'll move to some questions. So coming to channel routing. So in channel routing, the changes in the shape of the hydrograph as it travels down a channel, we study that. Okay. So how the shape of the hydrograph is changing as we travel to the downstream. So let's see if this is the basin, right? And let's say this is the location of gauge 1. This is the upstream section, upstream side, right? Because this is the outlet we consider. And let's say here you have gauge 2. Okay, so what we'll study here, we'll study the change in the shape of hydrograph downstream, right? So let's say here you know the hydrograph, maybe something like that. Here you need to understand that what will be the hydrograph. So if the input hydrograph at the upstream end of the reach is known, this form of routing aims to predict the flood hydrograph at various sections of the reach. Okay, so this channel routing will help you to understand or obtain the information about the flood peak attenuation, also the duration of high water level. I'll write that. Flood peak attenuation and duration of high water levels. Right? Okay, so we'll do some questions and then again we'll come back here. Okay, so the first question is reservoir routing is important for. I'll give you guys a few seconds for this. We have just discussed this question. Any guesses? So we have seen that we do reservoir routing to understand the or to know the location where we need to do the construct the reservoir. And not only that, but to understand the capacity of the reservoir, not only the shape or the size, how much will be the capacity of the reservoir, and so on. So the correct answer will be both A and B. Right? Any question here? If not, we'll move to the next question. So the next question is compared with the inflow hydrograph, the peak of the outflow hydrograph from a reach is usually. So we have seen, right, that let's say if we have a hydrograph with discharge or let's say flow versus time, and let's say if this is the inflow hydrograph and let's say if this is the outflow hydrograph, something like this maybe. Okay, so we have inflow hydrograph and outflow hydrograph. So the question is, compared with the inflow hydrograph, the peak of the outflow hydrograph from a reach is usually in terms of in terms of everything. So here you can see the peak of inflow hydrograph is here, peak of outflow hydrograph is here. It is attenuated firstly. So the option 1 is correct. Again, in the time domain, if you see, it is delayed because it is comparing from the peak of the outflow hydrograph, right? So answer will be both A and B, right? Any doubt here? Okay. Okay, so the next question is the equation used in the hydraulic routing. Okay, so in this we meet and then we'll come back. Yeah. So now we'll move to the routing methods. So the routing methods again is classified into two groups. First is the lumped or hydrologic routing or hydrological routing, whatever you see. And second one is the distributed routing, or sometimes it is referred to as hydraulic routing. Okay. So what is the main difference between this lumped and distributed system routing? The main difference between this lumped and distributed system routing is that in a lumped model or in a lumped system model, the flow is calculated right here. Flow is calculated as a function of time alone, okay, at a particular location. The particular location. Okay. And whereas in the distributed routing, you will see that flow is calculated as a function of both time and space. Function of both space and time throughout the system. Okay. Now this lumped or hydrologic routing and distributed and hydraulic routing, there is one more difference between these two. That is, in the lumped or hydrological routing, in the hydrologic routing, or maybe the lump routing, I'm not writing it again. It considers the equation of continuity. Okay, whereas in hydraulic routing, both the equation of continuity equation of continuity and momentum is used. Okay, so it is also called for the unsteady flow. Unsteady flow. Okay, so mostly in this hydraulic routing, we have to solve partial differential equations. So let's say if you would have studied open channel flow or fluid mechanics in your graduate or something, then you might have seen that we use the partial differential equation for open channel flow. Those are solved. Okay, so we'll start with the hydrologic routing or the lumped flow routing. Okay, where it is only function of time at a particular location. and which equation is considered? Only the continuity equation is considered, right? So hydrologic routing. So mostly the flow that we consider here is gradually varied, sorry, unsteady flow, right? So gradually varied unsteady flow is like the flow which does not which changes with time, and but it is in this page if you see the flow is varying gradually. Okay, so these terms, the gradually varied flow, steady flow, unsteady flow, non-uniform flow, these you might have studied in fluid mechanics. I'm not reiterating that here. Okay, so what I said, that in this hydrologic routing we consider the equation of continuity, right? So mostly we consider simple mass balance equation, or if you say water balance equation, whatever you say, right? So it is like inflow minus outflow will be equals to the change in storage. Change in storage, correct? That is, if we write I inflow as I, outflow as O, change in storage would be ds dt. Okay, so I is the inflow rate, O is the outflow rate, and S, only if you consider S is the storage. Okay, and ds dt is the change in storage. Okay, so this equation, this mass balance equation only is considered in different forms when you are using in wherever you are using based on that. Okay, so let's say if a small time interval is considered, let's say del t is considered between the total inflow volume and the total outflow volume, then how do we write? We write that as I bar into del t minus O bar into del t equals change in the storage, where I bar is the average inflow, right? And O bar is the average outflow. Okay, and del t I said that it is a very small time interval. Okay, and del S is the change in storage. Again, if you see in the form of finite difference or something like that, so in that case it will be this equation. See, this is the average inflow, right? So we can write that as like I1 plus I2 by 2. So it can be like the beginning inflow and the final inflow. Okay, I1 and I2 is like beginning or inflow and final inflow. So I1 plus I2 by 2, that is the average one, into the small time interval, that is del t, minus O1 plus O2 by 2 into del t, that is equals to S2 minus S1, right? So as I mentioned, that 1 here denotes the starting or the beginning of the time interval del t, and 2 is the end of the small time interval del t. Okay, so you should remember that this time interval, that is del t, should be sufficiently short or small to avoid large variations in the discharge over it. So let's say if in a very small interval, if there is a very vast changes, we can't consider that. We have to consider very small, or we have to go to some other routing method. Or else, let's say if in a very small interval that we are talking about, the variations are not very large, we can consider this method. Okay, otherwise we'll move to the hydraulic routing. Okay, we'll move to the hydraulic routing. As I mentioned that in hydraulic routing we consider both the continuity equation and the what do you say, momentum equation. right? So in the lectures we have gone through all those things, like what are the continuity equation, and what are the momentum equation, the differential form of the equation of continuity, like for unsteady flow in a reach, right? So we have seen all that. And then equation of motion for a flood wave is also derived from the application of momentum equation. So applying both the continuity equation and momentum equation, we get the Saint Venant's equation. So Saint Venant equation will come again, okay, in some time. Just for now, just to know that we come to Saint Venant's equation using both continuity and momentum equation. Okay. So now in the hydrologic river routing, mostly what we need, we have space here. So in hydrologic, I will write it next page. Right. So we have seen that for reservoir routing, what all we need the storage elevation curve for the reservoir, and we said that for any of the reservoir we will get the storage elevation reservoir. Next we need the outflow elevation relationship, or the outflow elevation curve for the outlet structure, right? And other than that, we need the inflow hydrograph as well as the initial elevation. Because see, initial elevation before one flood, we will know that okay, this much water level it was before this flood, because we are anyway continuously monitoring the elevation and recharge value. So inflow hydrograph and initial elevation will know. From the relationship of the storage elevation, we'll have the storage elevation curve, and other than that, we need the outflow elevation curve from for the outlet structure. Now, if you see the first two, storage elevation curve and outflow elevation curve, from this, that is storage elevation and outflow elevation curve, you will get a relationship of storage versus storage versus outflow, isn't it? Right? So this one will need. Okay, this one will be in the x-axis. This one will be in the y-axis. Okay. Right. Yeah, and one thing I was mentioning here was, see this part. Maybe which part I should have. So let's say this part, the inflow hydrograph and the outflow hydrograph, this part and this part. So second part that we see, so let's I'll write this as second part and this as the first part. The first part what we have, first part, see inflow hydrograph is starting and outflow hydrograph is starting. So the whatever remaining will be there, here what will happen? The reservoir storage will increase, right? And now when the both both of them are joining, after that what will happen? The withdrawal will happen. So withdrawal from the storage, and remember that area of 1 will be equal to area of 2. Okay, both the area should be equal. Okay, So with this, we'll do some questions and then we'll come back. Okay, so the next question is the equation used in hydraulic routing is. So we have just seen then that for 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 hydrologic routing we consider only the continuity or the mass balance, right? Continuity equation. Whereas for hydraulic routing we consider both the continuity and momentum equation, right? So the correct answer for this will be both the continuity and momentum equation we use, and hence answer will be both A and B, right? Okay, so the next question is which of the following relationships should be known to predict the reservoir elevation and outflow variations with time using the reservoir routing? So what is the question that we are doing the reservoir routing, right? And which of the following relationships we should know to predict the reservoir elevation and outflow variation with the time? So we just now we have seen that which what all we need for the reservoir routing. We need the storage elevation curve or a storage elevation relationship, right? Next, what we need the outflow elevation curve, right? So for it, so here what is there that which of the following relationship should be known to predict the reservoir elevation and outflow variations? What we need? We need the outflow versus or discharge versus elevation reservoir. So the options are discharge elevation relationship of the reservoir. Second option is inflow stage relationship of the reservoir. Third is the outflow elevation relationship of spillway, or the fourth is the volume elevation relationship of spillway. So the correct answer will be C, that is outflow elevation relationship of the spillway. Remember where we have mentioned, there I have mentioned that we have the outflow, see, outflow elevation curve for the outlet structure. So here the outlet structure is what? The outlet structure is the spillway. Okay, so the correct answer will be C, that is outflow elevation relationship of spillway. Okay, yeah. So the next question is the average inflow and outflow rates from a reach are 34 meter cube per second and 27 meter cube per second, right? So you have to find out the change in storage in the reach in a time interval of 11 seconds, right? So we have given the average, sorry, the average inflow rate is given as 34 meter cube per second, and average outflow rate is given as 27 meter cube per second, right? You need to find out the change in storage where delta is given as 11 seconds. I'll give you 1 minute for this. You guys can try once. Okay. Anyone? Anyone got anything? If not, I'll do that. So, simple mass balance equation we have to use, that is I bar minus O bar is equals to del S del T, right? So we can write this as del S is equals to 34 minus 27 meter cube per second into 11 seconds. So whatever we'll get in the meter cube per second. Okay. Because both the inflow and outflow are the average inflow rates, right? So 34 minus 27, so sheds 7, that is 77 meter cube per second. Right here you can see that the inflow or the average inflow rate is higher than that of the outflow average outflow rate, right? So here what we have, the change in storage will have a gain, right? Because let's say if you have more inflow than outflow, then what will happen, the storage will be more, or you can store the water more, and hence we have a gain of 77 meter cube per second. Hence the answer will be B, that is gain of 77 meter cube per second, or between the 77 meter cube. Okay. Okay. So next question is, during hydrological routing of a reservoir, the time to peak of flow inflow hydrograph was found to be T hours. Which of the following is the most likely time to peak for the outflow hydrograph? So this is a very easy questions that we have just seen, right? So let's say if this is the discharge versus time, Q versus T. We have seen, let's say this is the inflow hydrograph, and this is the outflow hydrograph. Then what you can see here, that during the hydrological routing of a reservoir, the time to peak of inflow hydrograph was found to be T hours. Okay, so let's say this is the time to peak, this is T hours. Okay, now the question is, which of the following is the most likely time to peak for outflow hydrograph? So this one is the question. Okay, so the first is T minus 2 hours. T minus 2 hours will be somewhere here, right? This one will be T minus 2 hours. Okay, so we know that there will be a delay in the peak of outflow hydrograph with respect to the inflow hydrograph, correct? And hence whatever time of peak will be there for inflow hydrograph, the time to peak for the outflow hydrograph will be more than that. And hence you see a option A, that is T minus 2 hydrograph hours or T hours or 0.5 T hours. All these are less than that of, less than or equal to time to peak for inflow hydrograph, right? But this, that is 1.5 into T hours, this is more than that of the T hours. Hence the most likely time to peak from of all these options will be 1.5 T hours. So hence the outflow hydrograph peak will happen at around 1.5 into T hours, correct? Any questions here? Okay. So the correct answer is D, that is 1.5 into T hours. Okay. Okay. So we'll move to the next question then. So the next question is, which of the following is not an assumptions in the pulse method? Okay. Okay, so we'll just see the pulse method or something. Then again we'll come back. Okay, so next we have pulse method, or we call that as inflow storage discharge method. Okay, so this is one of the hydrologic reservoir routing method. Okay, so other than the pulse method, what we have modified pulse method, which we call as level pool routing also. Okay, so we'll see that. So the equations and all we have seen in the lectures. So mostly what we have, we use the basic hydrologic equations only. that is, where is that, this one, right? So the routing, how do? We substitute the known values in the equation to obtain. So we just, okay, I'll write that. What we do, we just reshuffle these terms, and we write this equation, that is I1 plus I2 by 2 into delta, this equation in the form of I1 plus I2 by 2 again into delta plus what we do, the known value, that is S1, because the storage, S1 is what, storage at the beginning of the flow or the flood, right? So S1, and what all we need, we know the outflow also at that time, and what we do, we take all those things in the right hand side, that is, sorry, left hand side, S1 plus, sorry, S1 minus O1, S1 minus O1 into del T by 2, and the remaining unknown will keep it on the right hand side, that is S2 plus O2 into del T by 2. What? We just use the same equation, we just reshuffled it based on whatever is known to us. Okay, and routing, what, how do we do? We substitute the known values in the equation, because so all these are the known values. Okay, we substitute all this value to get to this unknown term, that is S2 plus O2 into del T by 2, and then we obtain this O2 from the relationship, that is outflow versus storage, right? So what we need, we need the outflow versus storage relationship for this. So we have seen that in the beginning also, that here, see, outflow elevation curve, we have the storage elevation curve, from that we get the storage versus outflow curve, and that is what we need, we will use here to get to this O2. Okay, yeah. Now coming to the assumptions of the pulse method. Assumptions, what all assumptions it does, it considers that the reservoir surface or reservoir water surface is horizontal. Yeah, this means it can be applied in reservoirs or streams, something like that. Next, it considers that outflow is a unique function of storage volume, and that's how we get the relationship of outflow and storage volume, right? And it also considers that outflow rate varies linearly with time. Okay, so from these assumptions only you can see what are the limitations of these method. Can you tell me what, anyone? So you can see this is applicable for the applicable when the reservoir water surface is horizontal, and hence when there is a sharper gradient, like let's say 0.57 meter per kilometer, then we can't use this pulse method or inflow storage discharge method. It is also not suitable for river or channel breaches with time varying boundaries. That's, let's say if tides happen, or if there is a rapidly changing hydrographs for, let's say, dam breaks and all. For that case, we can't use this pulse method. Okay. So in this, what we need three curves, or so let's say what we do, we get three, this curve I was talking about relationship, right? So if you just see, let's say this is in the meter cube days, let's say meter cube per second days, and this is the outflow in cubics. This is what storage change in the volume. So you need three curves for this method, that is pulse method. So this one will be S minus O into del T by 2. This one will be only S, and this one will be S plus O into del T by 2, right? So from this, all these relationships, you will get to the outflow, and hence you can create the outflow hydrograph. Okay. Next, what we have? We have the modified pulse method, or we call that as level pool method, level pool routing method. So most of the things are same. Only what is the modification that is happening in case of modified pulse method is we only need two curve in this. The assumptions and the limitations being the same, we need two curves. That is, one will be the S curve and another will be S plus O into del T by 2. The third curve that you see here, S minus O into del T by 2, we don't need here. Hence, we use this modified pulse method or level pool method. Okay, the numericals and all is done in the class. I'm not deep into that. Okay, if there is any concept questions, you can ask me here. Any questions on these methods and all? Okay, if not, we'll move to the hydrologic channel routing. So till now we did the hydrologic reservoir routing, right? Now we'll move to the hydrologic channel routing. Right, remember we are still doing the hydrologic routing, hence we are only considering the continuity equation. So hydrologic channel routing is used to model the movement of water through the river channels or other conveyance system. Any, let's say any conveyance system, pipe and all are there. There also we can use this routing. So what we considered here, so let's say you have one conveyance system, something like this. Right, so this is the inflow, let's say. Okay, but the outflow is somewhere here. Okay, so this is the outflow. Okay, so here this is the outflow. Okay, so what we see here, we see the movement of flood wave in a stream channel is, so we know that movement of a flood channel or flood wave in a stream is highly complicated phenomenon, right? Because uh, the flood wave, how it behaves in a stream, it will be a unsteady and non-uniform flow, right? Unsteady, unsteady and non-uniform flow. That is, the flow will vary with time, and it will also be varying in terms of space. Okay. So beside the flow varying with time as the wave progresses downstream, the channel properties and inflow also vary, right? And that's how it is non-uniform flow. Okay, and hence the analytical solution to the problems becomes complicated. Hence we go for finite difference and so on. Okay, and hence a different approach is adopted, as I said, that the channel storage is expressed as a function of the channel storage. Let's say S is defined as a function of both inflow and outflow in case of channel routing, hydrologic channel routing. And remember, in reservoir routing, what we consider? We consider only the storage change as a function of outflow only. Okay. So for this, uh, there is Linsley. He gave the storage channel could be considered. This storage change can be considered as the sum of two portions. That is prism storage and the wedge storage. Okay, the Linsley has considered two parts. So if you have seen, let's say if this is the store, maybe the ground surface or something like that near this, and the flow happening something like this. So it considers two things. Let's say if you just draw it like this, So wherever the flow you can see, if it is in the form of prism, let's say, right? So this is prism or the third part where it is joining. This is the prism part. This is the prism part, right? Now you see this part is not in this prism, but we have considered that also. This is the wedge part. Okay, and this is the negative wedge part because we have considered that as in prism. Whereas if you see this part and this part, these two also are wedge storage, but as we have not considered this in prism, it is a positive wedge storage. Okay, and this is the water flow that is happening. So what Lindsley considered? Lindsley considered that this change in storage is the summation of both the prism storage plus wedge storage. And what is this prism storage? Prism storage is the volume of water that is stored below an imaginary line. So this line that you can see, how to differentiate? Let's see. Black color here. Right? So that's black color you can see. This is the imaginary line. Now, the volume of water that is stored below an imaginary line drawn parallel to the channel bottom, starting at outflow section, water surface, we call that as prism storage. And what is wedge storage? Wedge storage is the volume of water between the imaginary line and the water surface profiles. Okay. So we have just defined the wedge storage and prism storage. I hope this is clear. Any questions here? So what can you tell me that with this whatever concept we have learned just now, the prism storage, if you write the storage, prism storage, if I write it as SP, this is, if you see, it is a very similar thing that we have considered in the reservoir routing, and hence it will be a function of outflow only. Whereas if you see the if you see the wedge storage, wedge storage, that is SW if I write, this is the function of inflow only, correct? And hence the consideration that we had that the storage is the function of both inflow and outflow is met in this. Hence the prism storage, if you see, it remains constant at a fixed depth at a downstream section, while the wedge storage changes from positive value at an advancing flood to a negative value during the receding flood. So wherever there is a receding flood, it will have a negative wedge, and wherever there is a advancing flood, there it will be a positive value of the wedge storage. Okay. So generally, how we consider this storage? The storage is written something like, in a general expression it has written, where this S is considered something as X is a weighing factor, X into B into I by A to the power M by N plus 1 minus X, because X is the weighing factor, right? Into B into O by A, where O is the outflow to the power M by N. Okay, so this is a general expression where A and B are constant, X is the weighing factor. Okay, so for a uniform flow, so let's say if there is a uniform flow in a prismatic channel, so it is a whole like prism kind of structure, prismatic channel, it is given that M will be equals to 1 and N equals to 5 by 3. Therefore, in this equation you see we have M by N only, right? So M by N will be equals to 0.6. Okay, and for natural channel it will exceed 1. So the value of M by 1 will be more than that of 1. Okay, and you see the weighing factor here, weighing factor, that is X. So this, if the storage is a function of outflow only, sorry, if the storage is a function of outflow only, that is in the case of reservoir routing, then X will be equals to 0. Okay, however, for natural streams, X will vary from 0 to 0.4 naturally. Okay, So for hydrological channel routing, we mostly so for hydrologic channel routing, the method that we mostly use is the Muskingum method. Okay, so in Muskingum method, what we do, the assumptions that we assume that the flow in a river channel is influenced by the is influenced by what all? It is influenced by the channel storage, then the inflow hydrograph and the outflow hydrograph, right? And it also assumes that m by n will be equals to 1 and b by a, the constant that we have seen there, is equals to k. K is also constant here, okay? And hence the expressions becomes this general expression you can see, right? X into b into I by a to the power m by n, something like that. This reduces to S is equals to k into xi plus 1 minus x into O. O is the outflow, okay? Where k and x are the routing constant. X is the weighing factor and k is also the routing constant. Okay. So if you see the wedge, or let's say again if I draw that, I'll draw it here again so that it is more clear. Okay. So we have seen this is the inflow and this is the outflow. See this part that you can see, the upper part of the outflow part. This is the wedge storage, right? Now if you compare with this equation, the wedge storage will be which one? It will be k into x into I minus O. Okay, that is kx into inflow minus outflow. Whereas this part, that is the only the prism part, it will be, that is the prism storage. How you can write this? It will be equals to k into O, right? So if you consider the continuity equation of that we have seen, and this equation, that is s equals to k into xi plus 1 minus x into O. So the outflow equation that you will get, O2 is equals, would be equals to C naught into I2 plus C1 into I1 plus C, sorry, okay, yeah, C2, C2 into I naught. Just remember that with C naught we have I2, C1 we have I1, and C2 we have I naught. Okay, so many times we do mistake, we write it as C0 I0 plus C1 I1 plus C2 I2. So just don't do that mistake. Where this C and all these three C are the constant. How do we write that? C naught will be equals to minus k into x plus zero point 0.5 into del t. Remember, I was talking about del t, that is a very small time interval. So this is what del t is. K minus kx plus 0.5 del T. Then C1 will be written as Kx plus 0.5 into del T divided by K minus Kx plus 0.5 into del T, and C2 will be equals to K minus Kx minus 0.5 into del T divided by K minus Kx plus 0.5 into del T. One thing you will note here is, let's say if you add all this C0, C1 and C2, you see all the denominators are the same, right? If you just add all this C0 plus C1 plus C2, what you will get? As the denominator is the same, you can write it as K minus Kx plus 0.5 into del T, right? And the first will be Kx plus 0.5 into del T. C1 it is Kx plus 0.5 into del T, and third is K minus Kx minus 0.5 into del T. You can just cancel this out, and the remaining that you have is K minus Kx plus 0.5 into del T. The denominator also is the same, that is K minus Kx plus 0.5 into del T, right? And hence always this equation, that is C0 plus C1 plus C2, will be equal to 1, right? So this one will act as a check for whenever you are solving this routing problem. Okay, so how to deal with it we have just seen in the lecture. We'll go to some of the assignment questions now. We'll see how to do that, and then we'll come back again. Wait here. Okay. So the next question is, which of the following is not an assumption in the Puls method? We guys just did the Puls method. Can you just tell me what which like assumption is not the valid assumption in the Puls method? So we have seen that reservoir water surface should be horizontal. This is one of the assumptions in the Puls method. Then it is applied for with the outflow as a function of storage volume. Outflow rate should be varying linearly with time. And as this reservoir water surface is considered to be horizontal, obviously there will be no gradient in it, and hence it cannot be applied for streams with sharper gradient, and hence this is not an assumption in the Puls method. So the correct answer will be B, right? Okay. The next question is, the storage indication method is, okay. So the modified Puls method is also called as storage indication method. So this storage indication method is also called as modified Puls method or the level pool routing or level pool method. Okay. And in this modified Puls method, what we do, we construct only two curves. Remember the difference that I said between Puls method and modified Puls method is, in Puls method you consider three curves, and in the Puls method you only consider two curves. One is the S curve and another is S plus O into del T by 2 curve, right? And hence this storage indication method also uses requires construction of only two curves. So the correct answer here will be all of the above. That is, it is a modified Puls method, it is a level pool method, and it is a method which requires only construction of only two curves. So the correct answer will be D. Okay. Okay. Next, we'll move to the next question. According to Lindsley's theory, the volume of water between the imaginary line and the water surface profile is called as. You have seen that, right? Anyone? Any guesses? Guesses are not required anyway because we have just seen that. So the volume of water between the imaginary line and the water surface profile is called the wedge storage, right? So the correct answer will be B. Okay. The next question is, the wedge storage is a function of, remember, we saw that prism storage, we wrote that as SP is a function of outflow, like same as that of the reservoir routing. Whereas the new term, that is wedge storage, we wrote that as a function of inflow only, right? And hence the total term, that is S, is a function of both inflow and outflow. How? That is by SP plus SW, right? So the correct answer, the wedge story is a function of inflow only. So the correct answer would be A, right? So the correct answer would be A, inflow hydrograph. Okay. Okay. Next question is, for uniform flow in a prismatic channel, the value of n is generally taken as, we know, for uniform flow in a prismatic channel, we consider m by n as how much? Anyone? Just now we have seen, right? See. Yeah, here. For a uniform flow in a prismatic channel, we wrote m is equals to 1 and n equals to 5 by 3. That is m by n is equals to 0.6. Sorry. So m by n will be equals to, sorry, okay. M by n was 0.6, but we need only value of n. So n, it was given as 5 by 3, right? Or 3 by 5, something like that. Let me check this. It was 5 by 3, I think. Yeah, 5 by 3. So the correct answer will be 5 by 3 in options. Yeah, so 5 by 3 is 1.67. You can write that as 1.67. And hence the correct answer for this will be C, that is 1.67. Okay. Next question is, the Muskingum method of routing assumes the ratio of m by n as 1. We have seen that. Consider the ratio as 1. That is, option A is the correct answer. Okay. Wait. Yeah, the correct answer will be 1 only, because Muskingum method considers it as 1 only. So if this B is wrong, it will be A. Okay? Yeah. So the next question is, okay, the range of uh, the range of weighing factor X for natural streams varies from, we have seen that it varies from 0 to 0.4. Right? So these are information just given. The correct answer would be C, that is 0 to 0.4. Okay. Next question. In Muskingum equation of outflow, Q2 is equals to C0I2 plus C1I1 plus C2Q1. The sum of the three coefficients, that is C0 plus C1 plus C2, should be, we have just seen, it will be equals to 1. So the correct answer would be B, that is 1. Right? Any questions till now? Okay. Next question is, on the right hand side of the equation, that is S equals to KQ plus KX into I minus Q. Here remember that Q here, whatever we have written as O is the Q here, Q is the outflow, S is the storage, X is the weighing factor, and I is the inflow. The part that describes the wedge storage, we have seen that, right? Yeah, here. You see the wedge storage is what? It is K into X into I minus O. Okay, so the correct answer for here it will be wedge storage will be K into X into I minus Q. So this part of this equation, this is the wedge term, whereas this is the prism term. Correct? Okay, so the correct answer will be B, that is Kx into I minus Q. Okay, okay. Let's move on to the next question. The question is, what is the value of the smallest Muskingum routing coefficient for the storage time constant of 10 hours? So storage time constant as in K is the 10 hours. Then weighing factor X is given as 0.3 and interval del T is given as 6 hours. Just calculate all the routing coefficient and tell me how much you are getting for the smallest Muskingum routing coefficient. We'll give 1 minute for that. Anyone did? I'll do that. So we have written C naught as minus kx plus 0.5 into del T divided by k minus kx plus 0.5 into del T, right? So just put the values. K is minus 10 hours into x is zero point 0.3 plus 0.5 into 6, so it will come as 0. 10 minus 10 into zero point 0.3 plus 0.5 into 6, that is equals to, it will come as 0 by 10, that is 0. Okay, so if you just calculate C1 and C2 also, you can just check, it would be more than that. Okay, so let's say if 1 is 0, you can say that we know that C0 plus C1 plus C2 is equals to 1, right? Now if this is 0, these two will need to add up to 1, and if all these values are positive value, C1 and C2 should be more than that of 0. So even if you don't calculate these two, you can tell that C0 is the smallest Muskingum routing coefficient. Hence the correct answer would be 0. Okay, any question here? So the next question is, at a gauging station, flood data for the storm event is recorded at an intensity of 8 hours. Okay, so time interval is 8 hours, del T is given as 8 hours. Okay, find the Muskingum routing coefficient C0, C1 and C2 for routing this flood wave through a river reach with a storage coefficient of K equals to 12 hours and wing factor as 0.2. Just calculate all those values. C0 is equals to minus kx plus 0.5 into del T divided by k minus kx plus 0.5 into del T. I'll also do, you guys also do with me. Just check how much you're getting. 12 into 0.2 plus 0.5 into 8 divided by 12 minus 12 into 5 into 8. You guys also do and tell me how much you're getting. Sorry. Somewhere near 0.117 and write this as 0.12, right? Next, C1 was what? C1 was C1 equals to, what is the formula? Let's just see, right? Kx plus 0.5 into del T divided by Q minus Kx plus 0.5 into del T. So the round denominator we have 13.6. Okay? So it will be 12 into 0.2 plus 0.5 into 8 divided by 13.6. How much we are getting here? 12 into 0.2 plus 0.5 into 8, 6.4. 6.4 or 13.6 near 0.47. Okay, and C2 will be equals to, C2 you can directly write as minus 1 minus C naught minus C1. You don't need to use those big equations. It would be 1 minus 0.12 minus 0.47, that is equals to 0.41. So correct answer will be 0.12, 0.47 and 0.41. Can you just check? C0 is 0.12. First and the last, then C1 is 0.47. Yeah, so the correct answer will be A. I hope this is clear, because this is simply putting the equation and then getting the values. Okay. Okay. We'll move to the next question. The conservation form of Saint Venant equation includes. So for that we need the kinematic equation. Okay. We'll go to the next part. That is the hydraulic channel routing. Okay, next we are moving to hydraulic channel routing, right? So in hydraulic channel routing, you remember in hydraulic routing we are considering both the continuity equation as well as the momentum equation. So in this hydrologic channel routing will involve modeling the movement of water through river channels during the flood events, and this process will help you predict the flood waters, how it propagates downstream and all. So it is based on the Saint Venant equations, which considers both the continuity equation. The continuity equation, I'll not go into very deep because it is clear in the lecture, but in the differential form we can write that as del q del x plus del a del t will be equals to 0, right? And the momentum equation in the conservation form, it was written as 1 by a into del q del t plus 1 by a into del x of q square by a plus g into del y del x minus g into s naught minus sf will be equal to 0. Okay, how we got to these equations and all, you can refer to any of the engineering hydrology book or Watershed hydrology book. Okay, in PTCHA also it is there. Okay, just to see here, so which all terms refers to what? The first term you see, the first term that you can see, this one, it accounts for the unsteady flow, right? That is the local acceleration term is this one. Next, this one is the one which accounts for the non-uniform flow. This means it is the convective acceleration force. Convective acceleration term. Okay. This G into dy dx is the pressure force term. Pressure force term. Okay, and this last one is the friction force term. See how what affects the friction? The surface, right? So here S naught is the bed slope and SF is the friction slope. Okay, and G is the gravitation term, the gravity force if you like. I'll write that also. G is the gravity force. Okay. And for non-conservation equation, what we do, the average flow velocity is dependent variable instead of the Q. Okay, and this form of the equation can be derived for a unit width of the flow within the channel where we consider that there is no lateral flow. Okay, so if we write in the form of non-conservation term, non-conservation form, then how do you write that? Anyone? We write that as del V del T plus V into del V del X. V is what? V is a average flow velocity, right? It is average flow velocity. Okay, plus G into del Y del X. So the term remains the same. That is what it denotes. Only in case of instead of U, we write it as in the form of average flow velocity. It is so 0. Okay. So if you just consider this term, this is the kinematic wave term. If you consider both this term from here to here, we call that as diffusion wave term. So, diffusion wave term. And if you consider the whole equation, we call that as dynamic wave equation. Okay. So this kinematic wave term is the simplest form of the distributed model. Because if you see, you can write that as G naught into S naught, G naught in G into S naught minus SF. That is, S naught will be equals to SF. That is, bed slope is equals to the friction slope. Whereas in diffusion wave, you consider both the friction term and the pressure terms, right? And the dynamic wave, it considered the full hydrodynamic model. Okay. So in wave equation, you consider the kinematic wave, which govern the flow when inertial flow and the pressure forces are not important. Only the friction term and the gravitation terms are considered. And whereas this S naught and SF is getting equal, are balanced, right? And hence it is applicable for steady uniform flow. Steady and uniform flow, correct? So mostly these kinematic waves are often used for short-term duration flood events, where the time scale of the event is relatively small compared to the time it takes for the flow to accelerate or decelerate significantly. Okay, so what happens? The acceleration of the flow or the deceleration of flow is not very rapid. It happens gradually in a very slow term, and hence we can consider that as steady or uniform flow, right? So for this case, the Froude numbers will be Froude number. You remember? You can write that. I'm going to take wave, right? Steady uniform flow. I wrote short duration flood event, right? And Froude number Fr is less than 2. Remember, Fr is equals to inertia force by gravitation force. So we have seen all these numbers, Froude number, Reynolds number, all those numbers, right? Okay, so if the Froude number is less than 2, we consider the kinematic waves will be considered, right? And next, we have diffusion wave and dynamic wave. In the dynamic waves, it will govern the flow when all the terms are considered. That is the inertial force, pressure force, all these terms are important. For example, let's say if a large flood wave is happening, in that case, you see inertial force will be there, pressure force will be there, gravity force and the friction force, everything will be there. And hence, in that case, we'll consider the dynamic wave. And this dynamic wave is necessary for scenarios with longer flow durations, where the time scale for the flow acceleration and deceleration becomes very more like much more significant. Okay, so in channels with steep slopes or complex geometry, where flow acceleration and deceleration are like significant term, in that dynamic wave models provide a more accurate representation of the flow dynamics, right? So if you consider the kinematic wave models, okay. Last term I think is the celerity term. What is celerity? Celerity or wave celerity you call. So let's say if a still water is there, okay, this is like still water is there. Now, if you drop one pebble or something here, so what will happen? A ripple kind of will be happening all over the water, right? Something like that. Now, what is happening? A wave is getting created. Wave means what? Wave means a variation in the flow. So first it was steady, there was no flow, let's say. Now after you put the rock in it, there is a variation in the flow. That is change in the flow rate or water surface elevation we call. And hence this, what is wave celerity? Wave celerity is the velocity with which this variation as in variation in the flow or wave travels along the channel. So here uh, if you drop the pebble, the waves that you can see here in the rounded form, we call that as wave salinity. This happens in the flow also if the flow is happening. Okay, so what is why we are talking about this celerity? Because celerity is that type of variable in which a variety of hydrological models and this flow adapting algorithms that simulate changes in the river discharge. And hence, so let's say for basin scale, it varies from 0.25 to 10 meter per second, because see it is a velocity and hence the unit is in meter per second. Okay, so kinematic wave model is defined by the continuity equation that we have seen. So let's say if you see the kinematic wave model, the continuity equation was the first one that we have seen, the differential equation, right? That is del q del x plus del a del t equals to 0, and the momentum equation is only the bed slope term and the gravity term and friction term, and from there we got S naught, whatever S naught, correct? We got S naught is equals to SF. Okay, so in the kinematic wave model, the momentum equation is replaced by the uniform flow equation. For example, for the Manning's equation, right? So Manning's equation, we know that V is equals to 1 by n earth bar 2 by 3 is the bar half, right? Now this S term will be replaced by the SF term or S naught term. Okay, and hence Q, you can write the continuity equation Q equals to A n into V, and from here whatever you need you can get. And remember this R can be written as A by P, where A is the weighted area and P is the weighted perimeter. Okay, now if you put all this here, you can write this A as alpha into Q to the power beta in this form. Okay, where beta will be 0.6 and alpha will be a one term, big term that you can just go through. Okay, and from this A you can find out del A del T and del Q del X also you can find out, and then you can just you can see that it will be a function of only, so after you put that here it will be a function of Q itself, only Q. Okay, and then comes this kinematic wave celerity part, where you can put the kinematic wave celerity small q, then you can just do the equation. Okay, so if you just see the final value, ck is the kinematic wave celerity, kinematic wave celerity. This is written as del x del t or del q del a. Okay, so if constant discharge is there, small q will be 0, and if flow rate is increasing at a rate of del q del x, then it will be equals to small q. Okay, and this is for kinematic wave celerity. And for dynamic wave celerity, what it will be? Dynamic wave celerity, it will be written as CD is equals to root over G into Y. This is for rectangular channel. Okay, and then we can see the motion of flood wave and all. We have seen all those in the questions. So now we'll jump to the some questions. I think that will be today's questions. Okay, so this we have done. Next question is, the conservation form of the Saint-Venant equation includes, you have seen it includes all these terms, that is local acceleration term, in the convective acceleration term, pressure force, inertial force, friction force, and all. So the correct answer will be all. Okay. Yeah, the Froude number in case of kinematic waves, we have seen that it should be less than 2. Okay, so the correct answer would be A, that is less than 2. Okay. Next question is, the velocity with which variation in flow travels along the channel is called the wave celerity. Just now we have seen. Correct answer would be B. Okay, so the next question is, for a kinematic wave model, the momentum equation can be written as, we have just seen that, right? It will be S not into, because let's say if you write this as 0, you can write this as S not equals to, sorry, S not equals to SF, correct? So the correct answer will be C. Okay, so the next question is, the storage and the outflow of an emergency spillway are related as S is equals to 6000 Q. Okay, so we have the relationship between the storage of the spillway and outflow as S is equals to 6000 Q. Okay, and S is in meter cube and also Q is in meter cube per second. Inflow, outflow, and storage at the beginning are assumed to be 0. This means I 0 O or Q 0 and S 0 is equals to 0. And the outflow rate from the reservoir at the end of 1 hour. So let's say if you consider that T as 1 hour, that is 3,600 seconds. The inflow is given as 500. 1 is equals to 500 meter cube per second. You need to find out the outflow rate. Can you just do it? I'll give 1 or 2 minutes. You just use the continuity equation. We have the continuity equation as, not the mass balance equation. Right? I minus Q is equals to dSdt, right? So I was how much? I is given as 500 meter cube per second. You can write 500. Q we need to find out is equals to dSdt. Right? dSdt will be equals to change in the storage. Storage at the beginning is how much? 0, and at the end like relation is 6000 Q. So you can write that as 6000 Q minus 0 divided by T. T is how much? 3600 seconds, because Q is in meter cube per second, right? So we are considering that as a second. From this equation, can you just use this and just give me the value of Q? Simple, right? 500 minus Q will be equals to 6636. 36 5 q by 3, I think, right? So q plus 5q by 3, 3 is 3 punch, and 8q by 3 equals to 500. That is q we will get as 500 into 3 by 8. Just into so this is 7.5, I think. Yeah, so I got something as 187.5. Anyone got the same answer? So the correct answer will be A, that is 187.5 meter cubes per second. Okay, yeah. Okay, so the next question is the movement of a flood wave in a stream channel is, we have seen that for the movement of a flood wave in a stream channel is unsteady and non-uniform. Okay. The dynamic wave celerity for a wide rectangular channel can be expressed as Ct is equals to root over Gy. So correct answer will be A, right? Okay. Next question is rectangular channel is 50 meter wide and has a Manning's roughness coefficient of 0.035. Calculate the bed slope. Okay, just do this. Considering flow velocity of 3.5 meter per second and kinematic wave celerity of 4.8 meter per second and the flow rate of 125 qmax. Give 1 minute to start off. So how do you write this kinematic wave celerity? Ck is equals to S naught to the power half divided by n into 5 by 3 into y to the power 2 by 3, right? Now you see kinematic wave celerity is given, it is 4.8 meter per second. Okay, and also this one is the kinematic wave celerity. Also we have depth of flow. The depth of flow, this y we need to find out first, right? This is y is the depth of flow. So depth of flow is written as y equals to, because see it is a rectangular channel, right? So you can write it as q by area, that is q by v into v. That is q is how much? The flow rate is 125 meter cube per second. This is q. This is ck. Right? This is the width b. Manning's roughness coefficient, this is n, and flow velocity, this is v. Okay. Yeah. So q is equals to. Oh, sorry. Oh, sorry. Wrong thing. Because q equals to AV, we will write from there itself so that you can understand properly. We know q equals to AV, right? So we can write q is equals to b into y into v. So y will be written as q by b into v, right? So q is how much? Q is here 125 qmax, that is meter cube per second. B is 50 meter, and v is how much? 3.5 meter per second. You don't have to change any units. Let's do it. I'm not doing it. It's fine. 45. Right? So we got the depth of flow as, we got y as 0.71 meter. Just put this in this equation. So Ck, what we have? Ck is how much? 4.8 meter per second, right? S naught is how much? Is it given? No, right? We need to find out, bed slope only we need to find out. So S naught to the power half into 1 by n is 0.035 into 5 by 3 into zero point 0.7 in 1 to the power 2 by 3. Just do this and tell me how much you are getting as S naught. I'll also do once. 4.8 into 0.035 into 3 divided by 5 into 7 multiplied by 3. Okay, this is S naught per half. So square of that we are getting somewhere near 0.02, that is 2%. So the correct answer would be D, that is 2%. Okay, any question here? Okay, if not, we'll move. Okay, so we are done with the questions today. Okay, so lastly we had Muskingum Cunge method also. We have seen that Muskingum Cunge method, right? So in Muskingum Cunge method, what we saw? So Muskingum Cunge routing method was proposed by Cunge based on the Muskingum method. So in this, the method incorporates the diffusion wave approximation, making it more suitable for simulating the routing of flood waves through river channels. And mostly it is used in hydrological as well as the hydraulic modeling for river flow forecasting, right? Yeah, so mostly we use the finite difference method, and we have the k and x for this, and hence from there the is carried out by solving those equations. Okay, and hence using the appropriate condition, the Muskingum Cunge routing method can be employed to solve kinematic wave or both the diffusion wave equations also. Okay, so with that we'll close the session here. Any question till now, or any question in the assignment questions? Anything? Okay, if not, we'll stop it here. Okay. Okay.